Section 13. Carbon dioxide absorption at the bottom of the atmosphere, BOA. We would like to understand how carbon dioxide's 15 micron band, here, could be 100% absorbing across the atmosphere. The 4.3 and 2.7 micron bands are also 100% absorbing, but not the 2 micron band. In physics, attenuation or extinction is the gradual loss of flux intensity through a medium through absorption or scattering, and we have this differential equation. Where capital Phi is the flux intensity, in our case from thermal radiation outward from Earth's surface, neglecting emission by the atmosphere. Z is distance through the medium, in our case, height from Earth's surface, so altitude. Alpha is the absorption coefficient, with dimensions of 1 over length. And L is the absorption length, with dimension of length. For our simplified analysis, we ignore what happens to the absorbed energy. It disappears. For the full atmosphere, we would have to account for thermal radiation by the atmosphere. If the absorption coefficient and absorption length were independent of altitude, they are not, the outward flux from Earth's surface would decrease exponentially with altitude, with the flux decreasing to 37% at the altitude that equals the absorption length. So, flux is horizontal. At Earth's surface, the flux is highest. As we go up in altitude, the flux decreases. When our altitude is equal to the absorption length, we're down to 37% of the flux, and then it continues to decrease with altitude. We will see that this is a reasonable approximation for infrared absorption by carbon dioxide's 15 micron peak wavelength at the bottom of the atmosphere. For a given absorber such as carbon dioxide, the absorption coefficient at a given radiation wavelength, lambda, is the product of the absorption cross-section, sigma, at that wavelength, sigma with dimensions of area per molecule, and the number density, n, of absorber molecules, with dimensions of molecules per unit volume. The absorption cross-section is a complicated function of wavelength, as we saw earlier. Sources say that the absorption length for carbon dioxide's 15 micron band at the bottom of the atmosphere is 10 to 20 meters. If so, flux intensity would fall below 1% and absorption be higher than 99% within 100 meters of Earth's surface. Our assumption that cross-section and concentration were independent of altitude would be valid within that 100 meters. Let's see what we can calculate. Let's calculate the number density of carbon dioxide molecules at the bottom of the atmosphere, which climate scientists refer to as BOA, at plus 15 degrees Celsius. For simplicity, we assume dry air. We assume ideal gas at 15 Celsius. We calculate the number of moles per cubic meter, 42.3 moles per cubic meter. We use Avogadro's number to calculate the total number of molecules per cubic meter, 2.55 by 10 to the 25 molecules per cubic meter. We use the 2022 value of 420 parts per million for carbon dioxide, and we get 1.1 by 10 to the 22nd carbon dioxide molecules per cubic meter at sea level at plus 15 Celsius for 2022. Let's start with the absorption cross-section at the 14.98 micron peak wavelength, whose absorption cross-section is about 5 by 10 to the minus 18 centimeters squared per molecule from the cross-section graph. The cross-section value is a complicated function of temperature and pressure as well as wavelength, and this graph is not for plus 15 Celsius and 1 atmosphere, so our calculation can only be approximate. Absorption length equals 1 over the product of absorption cross-section and number density. I calculated an absorption length of 0.2 meters for the peak wavelength, 8 inches. Impressively short, and at first I thought this was wrong, but I verified it multiple ways. An absorption length of 20 meters, 100 times higher, corresponds to an absorption cross-section of about 5 by 10 to the minus 20 centimeters squared per molecule. And that's about 4 to 6 times smaller than the smallest peaks visible on the graph. So, it seems plausible that the range from 14.5 to 15.5 microns could have absorption length of 20 meters or less and 99% absorption within 100 meters of Earth's surface. SpectraPlot is a useful tool to play with to understand absorption by a single gas at our choice of pressure and temperature. Let's use SpectraPlot to verify absorption length and 100% absorption. We will use that transmission is e to the minus absorbance, and that equals e to the minus length over absorption length. Though beware that sometimes the field of optics uses 10 as the base instead of e. The SpectraPlot tool graphs the spectral absorbance or transmission over a fixed length or thickness of absorbing medium with fixed temperature, pressure, and concentration. I graphed transmission through the bottom of the atmosphere at plus 15 Celsius with 420 parts per million carbon dioxide. The horizontal axis is wavelength from 13 to 17 microns. The vertical axis is transmission from 0 at the bottom to 1 at the top. 100%. Absorption is 1 minus transmission, so 100% absorption at the bottom to 0 absorption at the top. I used a fixed length of 0.2 meters for the red curve and 20 meters for the blue curve. So transmission for the blue curve is much less than for the red curve. When transmission for the red curve dips below 37%, the green dashed line, the absorption length for those wavelengths is less than 0.2 meters. So we see that the peak wavelength has absorption length of 0.2 meters, which agrees with our earlier calculation. Success! When transmission for the blue curve dips below the green dashed line, the absorption length is less than 20 meters for those wavelengths. So, for many small wavelength ranges between 14 and 16 microns, but not for the entire range. Next, I used 100 microns. A wide band has absorption length less than 100 meters at the bottom of the atmosphere. It seems plausible that the broad range from 14 to 16 microns could have 99% absorption within the 80-kilometer atmosphere. It is plausible that even 1 kilometer of lower atmosphere at sea level would be fully absorbing for 15 micron and 4.3 micron wavelengths for 420 parts per million carbon dioxide, and even for pre-industrial 280 part per million. Next, I set the fixed thickness of absorbing medium to 1.5 kilometers. I used the fixed temperature and pressure at the bottom of the atmosphere. This tool does not implement the temperature and pressure profile of the atmosphere, so the graph is only a rough check against previous graphs. Here we see zero transmission, 100% absorption between 14.2 and 15.8 microns, and absorption falling in the outside wings. This is consistent with our previous graphs, which had 100% absorption between 14 and 16 microns across the 80-kilometer height of the atmosphere. So, what happens when we continue to emit carbon dioxide and increase the concentration in the atmosphere for the next 1,000 years? The band that is 100% absorbing can't get any more absorbing. But the wings will get more absorbing, less transparent, with increased concentration. And the band that is 100% absorbing will get a little wider. The atmosphere will absorb a little more of Earth's thermal radiation than previously and will get warmer. The atmosphere will then radiate more thermal radiation. Some of that radiation will be emitted by water molecules. Some of the radiation emitted by water molecules will be in the water vapor carbon dioxide window and will escape the atmosphere. Half of that escaping radiation will reach Earth's surface. That will raise the temperature of Earth's land and oceans over the following 100 years until steady state is reached. But if we continue to emit carbon dioxide and methane, the eventual steady state temperature continues to increase. I created a separate supplemental video explaining how to use SpectraPlot to get different results, including to calculate absorption length and to see the absorption spectrum at the top of the atmosphere. I'm a little confused by the 2 micron wavelength and its weak absorption. Its peak absorption cross-section is 5 by 10 to the minus 21. I calculate the absorption length as 200 meters at sea level and verified this with SpectraPlot. It would be longer with increasing altitude. I would think that this would be 100% absorbing over 10 kilometers, even with altitude dependence, but graphs show it as about 50% absorbing from Earth's surface to space. If the average cross-section for the 2 micron band were smaller, 3 by 10 to the minus 22, the absorption length at sea level would be 3.3 kilometers. According to my math, this would be 90% absorbed, not 50%, from Earth's surface to space, so there may be some things I don't understand or haven't accounted for. such as absorption cross-section dependence on temperature and pressure. Section 14, Absorption versus Altitude. We should also learn, at least in general terms, how absorption changes with altitude. Reasons include understanding absorption when it is less than 100%, which is critical to human-caused climate change, understanding how thermal radiation by the atmosphere gets absorbed and how much reaches outer space, which is how climate scientists assess conditions and present their results. And this helps us when we come to use a different tool, MODTRAN, later in the course. Top of atmosphere, 80-kilometer altitude. Very little absorption occurs above 80-kilometer altitude. Climate scientists refer to top of atmosphere, or TOA. I will use 80 kilometers as top of atmosphere. Sometimes climate scientists use 70 or 100 kilometers rather than 80. When considering thermal radiation reaching the top of the atmosphere outward from Earth, we have to include thermal radiation emitted from all altitudes of the atmosphere, as well as thermal radiation emitted from Earth's surface, and absorption at each altitude of the atmosphere. Climate scientists use Schwarzschild's equation for radiative transfer. This is necessary for climate modeling, but more complicated than we want to deal with. I want to convey how conditions in the atmosphere change with altitude and then do a rough estimate for carbon dioxide's absorption length at the top of the atmosphere. Some of this may not interest you, so feel free to skip to the next section. The absorption coefficient at some wavelength is the product of the absorption cross-section and the number density. All quantities are functions of altitude. Carbon dioxide's absorption cross-section, function of pressure and temperature, is more complicated than we can handle. So let's hold that off for now and look at the number density. As usual, we will ignore clouds, even though they're important, and treat the atmosphere as an ideal gas. Real climate modeling must deal with clouds and rain. This graph, from data from 1986, shows the concentration of different greenhouse gases in the atmosphere as a fraction of the number of total molecules in the atmosphere at different altitudes. The vertical axis is altitude. The horizontal axis is the log of the relative concentration. The blue curve is for water vapor. Average concentration at the bottom of the atmosphere, lower right, is a little less than 1%, much smaller than nitrogen and oxygen, not shown here. The fractional concentration of water vapor falls by a factor of about 3,500 from bottom to top of the atmosphere. The dashed black curve is methane, whose fractional concentration falls by a factor of 12 from bottom to top of the atmosphere in this graph. But the fractional concentration of carbon dioxide looks to be independent of altitude below 80 kilometers in this 1986 data. Carbon dioxide seems to have been well mixed in the atmosphere at the emission and removal rates at that time. We don't see a concentration gradient at the bottom of the atmosphere for the carbon dioxide or methane curves, even though we have been emitting faster than removal. I think this mixing is due to convection in the troposphere. Water vapor is different because it forms droplets and clouds and precipitates. Carbon dioxide molecules are said to remain in the atmosphere for hundreds of years to 1,000 years with no chemical reactions, while methane molecules get broken down in something like 8 to 12 years or so. And water molecules precipitate out in 10 days, but then get replenished by more evaporation. Presently, carbon dioxide gets removed slowly from the atmosphere by respiration by plants, particularly trees, and absorption by cold ocean regions, which makes oceans less alkaline, which is slightly misnamed as ocean acidification. Deforestation adds carbon dioxide to the atmosphere and decreases its removal rate, which increases heating. So, we can treat the relative concentration of carbon dioxide as independent of altitude, but a function of time. This is good for our simple calculations, but bad for climate change because carbon dioxide remains in the atmosphere so long, spreads out to all altitudes, can absorb at all altitudes, but only gets removed at Earth's surface, and only slowly. Carbon dioxide concentration was about 280 parts per million before the Industrial Revolution, was about 420 parts per million in 2022, and climate scientists really don't want it to reach 800 parts per million in the future. This graph shows how global average temperature, pressure, and density vary with altitude in the atmosphere. The green curve is air pressure, which falls rapidly with altitude. The red curve is temperature, which generally falls with altitude in the troposphere. Thermal inversion in cold Antarctica is a small exception not shown here. The temperature increases with altitude in the stratosphere due to absorption of solar ultraviolet radiation by ozone, which is created in the stratosphere by sunlight. Notice that the temperature at the top of the atmosphere is 100 degrees Celsius colder than Earth's average surface temperature, or 1/3 colder in Kelvin. The orange-brown curve is density, which falls rapidly with altitude. Here is a log linear graph of density, with altitude being the horizontal axis, altitude increasing to the right. Pressure and density are about 100,000 times lower at the 80-kilometer top of atmosphere than at sea level. And temperature is 190 to 200 Kelvin. Section 15, carbon dioxide absorption at the top of the atmosphere. Since density is about 100,000 times lower at the top of atmosphere than the bottom, and carbon dioxide fractional concentration is independent of altitude, we estimate that carbon dioxide absorption lengths would be about 100,000 times larger at the top of the atmosphere than the bottom, if the absorption cross-section were independent of altitude, but it is not. Absorption cross-section is a complicated function of wavelength, pressure, and temperature. For our purposes, the most important aspect is that a very narrow, tall spike at the top of the atmosphere gets broadened and shortened with increasing pressure at lower altitudes. So the purple curve here is the top of atmosphere. The green curve is at 50 kilometers. The blue curve is at 10 kilometers, and the red curve is at the bottom of the atmosphere. This is what happens to a single spike. There is a program for calculating absorption cross-sections as a function of wavelength, temperature, and pressure, called HAPPY for HITRAN, but I wasn't successful using it. I used the SpectraPlot tool to look at the top and bottom of the atmosphere. This tool does not output cross-sections, but it graphs absorbance and transmission over a fixed thickness of absorbing medium, which I set to 100 meters with fixed temperature, pressure, and concentration. This is the absorbance graph for the bottom of the atmosphere from 14 to 16 microns. The shape looks like our first absorption cross-section graph from PNNL. The peak absorbance is about 466, which gives an absorption length of 100 meters divided by 466, or 0.2 meters, which agrees with our earlier calculation. This is the absorbance graph for the 80-kilometer top of atmosphere, zoomed in to 14.6 to 15.4 microns. The smaller peaks are now narrow spikes due to lower pressure and lower temperature. The main peak is now resolved to over 27 narrow spikes. The absorbance has fallen greatly due to reduced number density due to lower density at the top of the atmosphere. The peak absorbance is about 0.59, which is an absorption length of 169 meters, almost 800 times longer at the top of the atmosphere than at the bottom. So, perhaps the absorption cross-section at the 14.98 micron peak wavelength increased by a factor of 127 due to low pressure and low temperature, but the number density decreased by a factor of 100,000. But the absorption length at the top of atmosphere for a different wavelength close to the peak wavelength, like here, may have increased by a factor of 1,000,000 or more relative to the bottom of the atmosphere. Radiation that escapes to outer space at one wavelength, like here, is coming from the top of the atmosphere, while a slightly different wavelength, like here, is coming from the troposphere. It's complicated. Here is the transmission through 1.5 kilometers at the temperature, pressure, and density at the 80-kilometer top of atmosphere, from 14 microns to 16 microns. This graph looks much different than our earlier graph at the bottom of the atmosphere. Instead of a wide band of 100% absorption at the bottom of the atmosphere, we now have sharp lines at the top of the atmosphere. Only about 50 narrow lines have absorption length less than 1.5 kilometers at the top of the atmosphere. There is no useful average absorption length for the 15 micron band at the top of the atmosphere. Emission. Here is a spectral plot graph of emission from 1 kilometer slices of the atmosphere at 2 altitudes, from 14.25 to 15.75 microns. The blue curve is at 10 kilometer altitude, and it looks like it's trying to be a black body curve. The brown curve at 50 kilometers is very spiky. This does not say where the radiation might get absorbed at higher altitudes. So for most of the 14.2 to 15.8 micron band, 100% of thermal radiation from Earth's surface is absorbed by the atmosphere, mostly at the bottom of the atmosphere, but thermal radiation emitted from different altitudes of the atmosphere could reach the top of the atmosphere and escape to outer space. Some radiation emitted by a carbon dioxide molecule at a given altitude might not get absorbed by carbon dioxide molecules at higher altitudes, where line widths are narrower and the number density is less, so that radiation escapes to outer space. Most of the escaping power in this wavelength range probably comes from the upper troposphere, but some wavelengths come from the stratosphere and mesosphere. It's complicated. I found differing accounts for the fraction of Earth's thermal radiation power that passes through the atmosphere and escapes to outer space. This source says 51%, but another source says 10%. I have not resolved this difference. This source says that of the greenhouse gas emissions by the atmosphere that escape to outer space, 84% of the power is emitted by the troposphere, 14% emitted by the stratosphere, and maybe 2% by the mesosphere. But I can't confirm these numbers. Section 16, 100% absorption. Why would additional emissions be bad? A confusing issue is that large portions of the 15 micron, 4.3 micron, and 2.7 micron absorption bands have nearly 100% absorption between the surface of the Earth and the top of the atmosphere. Adding more carbon dioxide to the atmosphere still increases heating, according to climate scientists. Why is this? Adding more carbon dioxide reduces the absorption length at all altitudes and temperatures, I think. I think this has 4 effects. Adding more carbon dioxide increases the absorption of wavelengths that are presently not 100% absorbed, such as the wings of the 15 micron band. This is the region within the golden and pink boxes in this image. The golden box, 13 to 14 microns, has a stronger impact than the pink box, 16 to 17 microns, because it is closer to the 10 micron peak of thermal radiation and has less absorption from water vapor. I think that increased absorption in the golden and pink boxes is almost all of the impact of continuing to increase carbon dioxide in the atmosphere. We will see this graphically later, and you can verify this for yourself with tools we will play with. There is still plenty of thermal radiation from Earth's surface to be absorbed. The red box is for methane, which also absorbs more radiation as concentration increases. Adding more carbon dioxide increases the width of the blanket wavelength ranges that are 100% absorbing, which increases absorption. I think this is a smaller impact than the wings with present concentration and emissions. For wavelengths for which the atmosphere is 100% absorbing due to carbon dioxide, reducing the absorption length raises the highest altitude from which there is 100% absorption to the top of the atmosphere for carbon dioxide wavelengths. If the radiation escaping to outer space was emitted by the troposphere or mesosphere, then increasing concentration moves the emission reaching outer space to a higher, colder layer of the atmosphere with less radiated power. The higher layer of the atmosphere has lower pressure and temperature, so the spectrum becomes spikier. In the stratosphere, temperature increases with altitude, which is more complicated. I believe the impact of this effect is low for carbon dioxide's 14 to 16 micron band, but we will revisit this later. Reducing the absorption length makes more of the re-radiation hitting Earth's surface, the back radiation, come from lower in the troposphere, closer to Earth's surface, which is generally warmer than the upper troposphere. This could result in more power being re-radiated to the Earth's surface and increased heating. But for carbon dioxide's 14 to 16 micron band, the absorption length at the bottom of the atmosphere is less than 100 meters. I believe the impact of this effect is minimal. Also, Antarctica has a thermal inversion in the lower troposphere, which should slightly reduce the impact. Continued emission of carbon dioxide will increase greenhouse warming, even though parts of the bands are already 100% absorbing. The incremental forcing and temperature increase due to additional carbon dioxide emissions decreases as concentration increases, as with a logarithmic curve. But that is no magic bullet. Additional emissions of carbon dioxide and methane still cause increased heating for decades and centuries after emission. And climate-related risks increase with every increment of warming. This pretty much completes the first half of this course. We now have a better understanding of the greenhouse effect and carbon dioxide's 15 micron wavelength band. Now we will look at the power absorbed by the atmosphere, increasing Earth's temperature, global warming. Section 17, Earth's Energy Imbalance, EEI. The Earth's energy imbalance is defined as the persistent and positive downward net top of atmosphere energy flux associated with greenhouse gas forcing of the climate system. The definition would be easier for us laymen to understand if it ended at the word flux. Downward minus upward radiation at the top of the atmosphere. Adding, associated with greenhouse gas forcing of the climate system, makes the definition sound confusing to me. It sounds like some net flux gets subtracted out. I don't know. So the amount of ultraviolet, visible, and infrared power incoming from the sun to the daytime disk of the Earth minus the infrared power radiated by the entire Earth and atmosphere outward at the top of the atmosphere, escaping to outer space, divided by Earth's surface area. Some visible light gets reflected back to space by clouds and ice and snow. The incoming power varies slightly seasonally and over years. The outbound radiation varies by location, temperature, cloud cover, and weather. It's complicated. Results get averaged over the Earth and over 1 or more years. In this graphic from NASA, more power is inbound than outbound at the top of the atmosphere. 0.6 watts per square meter more. If you take 340.4 and you subtract 77.0, 22.9, and 239.9, you get 0.6 watts per square meter. You get the same value if you calculate the net inbound power at Earth's surface. To reach balance, the Earth's temperature will rise and increase the outbound radiation. Here. However, once there is an imbalance, it takes hundreds of years to 1,000 years to reach balance due to the thermal inertia of Earth's oceans and, to a lesser extent, land. Climate scientists generally model, measure, and report radiation at the top of the atmosphere. Earth's surface has evaporation, precipitation, wind, and weather variation, and so is much more complicated than the top of the atmosphere. The troposphere is complicated by convection, clouds, and precipitation. Some results get reported at the top of the troposphere, but there are some clouds in the stratosphere. This energy imbalance of 0.6 watts per square meter is a 10-year average before 2010. One source said that the value grew from 0.6 to over 1 from 2009 to 2019. Another source said the value averaged 0.9 from 2005 to 2019. So the takeaway is a positive energy imbalance, increasing with time, of a little over 1 watt per square meter presently. This does not directly tell us the temperature rise. There are other energy budget, energy flow diagrams. They seem to each use different quantities with different values. I have not attempted to reconcile them. I wish there was one single tidy set of numbers for a given year. Section 18, absorbed and reradiated power. I cannot calculate Earth's energy budget imbalance or radiative forcing with simple physics and math, but we can calculate the thermal power available to be absorbed and potentially reradiated by the 13 to 14 micron wing of carbon dioxide's 15 micron band, with which we will have become familiar. I used Planck's blackbody spectral radiance formula. The results are in watts per meter cubed per steradian. Using a solid angle of pi steradians, a temperature of plus 15 degrees Celsius, and a 1 micron bandwidth, I got 21 watts per square meter available to be absorbed in the 13 to 14 micron range. If we were interested in a broader wavelength range, we can use this integral. Say that the carbon dioxide absorbs half of this power, thermalizes the energy across the spectrum, and then emits half of that toward Earth's surface in transparent window wavelengths. Maybe 5 watts per square meter would be re-radiated back to Earth's surface. This is larger than, but in the same ballpark as the change in immediate forcing that we will see reported by the ModTran tool in a little bit. So it seems plausible that the greenhouse effect of carbon dioxide's 13 to 14 micron wing is a significant enough component of Earth's energy balance or imbalance, even with 14 to 16 microns being 100% absorbing. This does not say the impact of additional carbon dioxide in the atmosphere, but we will cover that in the ModTran section. Section 19, Global Warming. Earth's energy imbalance greater than 1 watt per square meter and increasing. Climate scientists say that Earth is experiencing an energy imbalance of about 1 watt per square meter, excess radiation hitting the surface of the Earth, causing temperatures to increase to move toward steady-state balance. We can use the Stefan-Boltzmann law to see how much Earth's surface temperature would need to increase to send an additional 1 watt per square meter into the atmosphere. Let's crudely estimate that only half that additional radiation will escape to outer space, so let's double the temperature increase. I calculated an increase of 0.67 degrees Fahrenheit, 0.37 Celsius. This is simplistic, as climate is a complicated system with emissivity, albedo, thermal inertia, clouds, absorption, transmission, non-uniform, non-constant surface temperature, atmospheric conditions varying with latitude, altitude, and positive and negative feedbacks. Nevertheless, it is plausible that an additional watt per square meter absorbed by the surface of the Earth could raise the surface temperature by 1 degree Celsius. Earth's average surface temperature has increased by around 2 degrees Fahrenheit, or more than 1 degree Celsius, in recent decades. Climate scientists say that the temperature increase due to a step increase in carbon dioxide concentration takes hundreds of years to 1,000 years to reach the full value of temperature increase. due to the thermal inertia of the Earth's oceans and to a lesser extent, land. Since we continue to emit carbon dioxide each year, we laymen cannot match a temperature increase in one year to emission in prior years. This is also complicated for climate scientists. Section 20, Radiative Forcing, or RF. The Intergovernmental Panel on Climate Change, the IPCC, defines climate forcing or radiative forcing as the change in the net downward minus upward radiative flux expressed in watts per square meter due to a change in an external driver of climate change, such as a change in the concentration of carbon dioxide or methane, the concentration of volcanic aerosols, or the output of the sun. So, Earth's energy imbalance is a net flux averaged over the Earth and over some number of years, and radiative forcing is a change in that net flux, forcing changes in the climate. Often, the change being reported is relative to a given pre-industrial base year, such as 1750. But a change can also be relative to a specific prior concentration of greenhouse gases in the atmosphere, such as pre-industrial concentrations 280 parts per million carbon dioxide and 0.7 part per million methane. So, don't compare two radiative forcing numbers unless they use the same base. In a coming section, we will use the ModTran tool to model the change in radiative forcing between two concentrations of carbon dioxide. Also, a graph or data might include natural and anthropogenic human-caused sources, or just anthropogenic sources, or just long-lived, well-mixed atmospheric greenhouse gases, not aerosols with their strong cooling effect. So beware comparing numbers from different graphs or sources. Climate modeling models regional conditions across the entire Earth. I believe climate scientists generally report radiative forcing as the averaged modeled, not measured value for the Earth. But greenhouse gas concentrations, I believe, are generally measured. Climate scientists report their radiative forcing values either at the top of the atmosphere or the top of the troposphere, and those values will differ somewhat. We will use top of atmosphere when we use the ModTran tool in a later section. Very little absorption occurs in the atmosphere above 80 kilometers, so climate scientists use either 70, 80, or 100 kilometers as the top of atmosphere for reporting radiative forcing. I generally used 80 kilometers. The only heat transfer here is radiative, whereas convection, cloud formation, precipitation, and weather systems, large and small, occur in the troposphere, and evaporation occurs at Earth's surface. I believe that radiative forcing values at the bottom of the atmosphere are suspect if you see them in an article. Top of atmosphere has the advantage that satellites can record the radiation intensity inward from the sun and outward toward outer space. The IPCC summarized the current scientific consensus about radiative forcing changes as follows. Human-caused radiative forcing of 2.72 watts per square meter in 2019 relative to 1750 has warmed the climate system. This warming is mainly due to increased greenhouse gas concentrations. partly reduced by cooling due to increased aerosol concentrations. I don't see how to relate these radiative forcing numbers to the 0.6 watts per square meter value for the Earth's energy imbalance. Here is a 2022 breakdown of radiative forcing by emissions and drivers. We won't discuss this graph in detail, but I want to highlight that the uncertainty, this bar, the uncertainty for the cooling effect of sulfate aerosols changing clouds and helping to form smaller water droplets is large. More about water vapor later. Global temperature in 2023 was 0.2 degrees Celsius hotter than expected by climate models. A December 2024 article proposes that this may be due to reduced cloud cover in the lower troposphere, a reduction in Earth's albedo. That may be an unintended consequence of it intentionally reducing sulfur dioxide emissions by ocean-going ships to improve air quality, reduced haze, and acid rain. It's complicated. We cannot check these numbers with simplistic science and math, but going forward, let's remember that the uncertainties are significant but not dominant. Here is a different chart from 2011 with a different breakdown. The radiative forcing that has the largest magnitude is the forcing related to changes in the atmospheric global abundance of long-lived, well-mixed greenhouse gases, in particular carbon dioxide here and methane here, halogenated compounds, and nitrous oxide. This chart seems to suggest that the breakdown of methane increases atmospheric ozone, this green area. But I haven't found a source for that. I have not investigated the process that breaks down methane in the atmosphere. This chart reports the radiative forcing due to long-lived, well-mixed atmospheric greenhouse gases and does not include other contributions to radiative forcing such as ozone, positive forcing, and aerosols, negative forcing. The radiative forcing covered in this chart nearly doubled from 1979 to 2023. Carbon dioxide, the red bars, contributed 67% of the radiative forcing, and its forcing has slightly more than doubled since 1980. The red bars look to be a slow exponential increase due to continued emission. The second largest component is methane, about 16% of the forcing. Even though carbon dioxide concentration is 200 times higher. The methane component looks to have increased by 25% due to continued methane emissions exceeding the removal rate. Section 21. Climate sensitivity and feedbacks. An increase in concentration of greenhouse gases continues to increase Earth's global average surface temperature for centuries thereafter. If we stopped emitting carbon dioxide, the global temperature would continue to rise to a steady-state value in a few hundred years. The eventual increase of global temperature is not proportional to the concentration of greenhouse gases. The final temperature rise would be an approximately logarithmic function of the concentration when we stopped emitting, That is to say, each doubling of carbon dioxide concentration adds the same increment to the steady state temperature a couple hundred years later. This logarithmic character means that a given mass of new carbon dioxide emission in the future produces less additional warming than that already produced by the same mass of carbon dioxide emitted in the past, still present in the atmosphere. Each equal increment in concentration causes less warming than the previous increment, but each increment raises the global temperature further in the near term and hundreds of years later. Climate sensitivity is the term to describe how much warmer the planet will eventually get if the amount of a greenhouse gas in the atmosphere doubles, generally relative to the pre-industrial levels. This is also called equilibrium climate sensitivity, ECS. One source says that climate scientists agree that if there were no feedback effects at all, our climate sensitivity would be just 1 degree Celsius for a doubling of carbon dioxide. Another source says 0.75 degrees Celsius, which is what we will later get with the ModTran tool. So far, we have increased the carbon dioxide concentration by 50% over pre-industrial concentration, which would be a 0.6 degrees Celsius eventual temperature rise, 1 degree C times the natural log of 1.5 divided by the natural log of 2, if there were no feedback effects. And we have experienced something like 1.1 degrees Celsius rise so far, higher than prediction with no feedback effects. Rising temperature increases evaporation of water and the amount of water vapor the atmosphere can hold. Feedback effects from water vapor and clouds are important but quantitatively uncertain. Increased water vapor in the atmosphere, or increased cirrus clouds at the top of the troposphere, would increase heating of the Earth, but increased cumulus and stratus clouds in the lower troposphere would cool the Earth. Climate scientists say our climate sensitivity is very likely somewhere between 1.5 to 4.5 degrees Celsius, 2.7 to 8 degrees Fahrenheit, per doubling of carbon dioxide with feedback effects. So an uncertain amplification of 1.5 to 4.5 times from amplifying positive feedback effects. I was surprised that climate scientists haven't settled on a tighter range supported by measurements. This is complicated and unresolved. Some denialists claim that climate sensitivity should be 1 degree Celsius or less because the negative feedback from clouds should outweigh the positive feedback from water vapor. Mainstream climate scientists say that clouds produce negative feedback, but positive feedback from non-cloud water vapor outweighs the negative feedback of clouds. We laymen cannot resolve this. I can't check this amplified climate sensitivity at all. There is also large uncertainty in how much indirect cooling is produced by sulfate aerosols in the atmosphere. Aerosols allow smaller water droplets to form than would form in the absence of aerosols, which changes water vapor's feedback effect. So even more complicated and uncertain that we laymen cannot resolve. Emissions since 1800 or 1850 have increased atmospheric carbon dioxide concentration by 50%. The natural log of 1.5 divided by natural log of 2 is 0.58. So, we should get an eventual increase of 0.9 to 2.6 degrees Celsius over pre-industrial temperature with present concentration. We've already experienced the 1 degree Celsius rise, so the low end of the climate sensitivity seems suspect to me. There's a global goal to limit carbon dioxide to an additional 7%, though we will not achieve this. That 7% increment would produce an additional eventual increase in temperature of 0.15 to 0.44 degrees Celsius, or 0.26 to 0.8 degrees Fahrenheit. But achieving this would require great cost, difficulty, inconvenience, and political will, and we are not on track to achieve this. If we do nothing and continue to emit business as usual, temperature will continue to increase in coming centuries. If we reduce emissions too slowly, temperature will remain high for hundreds of years. If we could magically reduce emissions to zero, temperature would still continue to increase for the next 100 years, barring some unexpectedly large cooling effect kicking in. Methane is more complicated, as we will see at the end of the course.